The final condition that we're going to explore here is to see if it's sufficient enough that if a quadrilateral, a four-sided figure, has one pair of opposite sides that are congruent and parallel, then it's a parallelogram. Now this one's a little bit different, where it's the same pair of sides that are both parallel and congruent. So what's the deal if we have one pair of sides that are both parallel and congruent? Does it have to be a parallelogram? And that's what we're investigating, that's what we're trying to come up with. And in this case, that is a true statement, and what we're going to do is we're going to prove why that is so. So first of all, let me get our picture in line here, and what we're going to do is we're going to be given that ABCD is a quadrilateral, and that is given. And we are also going to say that we know that we got one pair of sides that are congruent and parallel. So I'm going to pick a pair of sides that are opposite, and we're going to make sure that we know that they are parallel congruent. So we know that AB is parallel to DC, and that AB is also known to be congruent to DC. And this is given in both cases. So this is what we start off knowing, and if we start off knowing this, then is it possible for us to prove that this is a parallelogram? Well, in order to prove this, it's a parallelogram, we want to basically come back and see if we can find out why these other two sides, AD and BC, would be parallel. So is it possible to prove that those are parallel is the next thing that we're going to be working on. And to do that, to establish that fact, we're going to bring in a diagonal, and we're going to work with some congruent triangles. And then we're going to use some corresponding parts and use those corresponding parts to help us prove that they are parallel. So starting off with this thought, we're going to prove that those two triangles are congruent. We already know it has a side on both one. We have the reflexive side here from DB to DB. And we know that these two sides are parallel, so we know that this alternate interior angle is congruent to that alternate interior angle, so I'll call it angle 1 and 2. So we know that the triangles now have to be congruent by side, angle, side. So we've got a side, an angle, and a side, angle, and a side in both of those, so the triangles are congruent. Well, if the triangles are congruent, then their corresponding parts have to be congruent. So now I'm going to pick on these corresponding parts. I'm going to name them 3 and 4. Angles 3 and 4 have to be congruent because they are corresponding parts of congruent triangles. And if that's the case, it forces the lines CB and AD to be parallel because 3 and 4 also happen to be alternate interior angles. And if alternate interior angles are congruent, then the lines are parallel. And then we end up with a figure that has both pair of sides that are opposite each other, parallel to each other. So there's the outline of the proof that I wanted to outline in front of you. Now we're going to put it down on paper. So BD is congruent to BD, and that was by reflexive property of equality. Since we were given a side that was congruent, put that in the wrong place. Given a side that was congruent, we already have that. We just named another side, and now we're going to go after our alternate interior angles. Angle 1 had to be congruent to angle 2 because they are alternate interior angles on parallel lines, so that's alternate interior angle theorem. So because we knew that these lines are parallel, it forced those two angles to be congruent. And that was enough for us to prove that our two triangles, so triangle ADB has to be congruent to triangle C, and then it's got to go BD, and that is by our side angle side congruency theorem. And because the triangles are congruent, then it forces some corresponding parts to be congruent, and that was angle 3 is congruent to angle 4, and that is by CPCTC. And because those angles were congruent, it forced lines AD to be parallel to line BC, and that was by our alternate interior angle theorem as well. The alternate interior angle theorem has been very versatile and very helpful in our proofs on these because it says if we know the lines are parallel, as in the first case, then angles 1 and 2 had to be congruent. And in the second case, since 3 and 4 had to be congruent by CPCTC, that forced the lines DB or DA and CB to be parallel, and therefore we know that this figure ABCD has to be a parallelogram by definition of a parallelogram, and make it the same parallelogram. So this is a condition that can prove that a four-sided figure has to be a parallelogram. So anytime you're given one pair of sides that is both congruent and parallel, it will have to be a parallelogram. So these are all things that we are going to use to help prove that a figure is a parallelogram. So let's recap some of the ways that we can do it. Number one, we can prove that one pair of sides is parallel and congruent. This was not a condition that worked. We had a counterexample for a kite. This one was not a condition, not a counterexample, was an isosceles trapezoid. But here's another one. If a quadrilateral has two pair of opposite angles that are congruent, it has to be a parallelogram. So we've got two ways of proving it's a parallelogram already. And our third way was if a diagonal created congruent triangles, it would have to be a parallelogram. So that's a recap. We had three different ways of proving that it's a parallelogram in a shorter way than what we had before. And we'll be able to use those now in other proofs to help prove that other objects end up being a parallelogram. So a little recap on what we were doing in the whole process in problem number 6.